Okay, so today we'll continue on our discussion of flow control. So we left off with if statements, and now we'll introduce else, which is not very exciting. I mean, it's important, but we'll do that. We got some loops, and then we'll start talking functions. Okay, and we probably won't get through everything, but we'll see how far we can get. Okay. So, yeah, we left off and we said in an if statement, you know, the code associated with the conditional in the if statement will only get executed if the conditional is true. We can expand this by using a curly brace and then using an else statement. The else statement will get executed when the if statement is false, okay? The else needs to be associated with an if, okay? Because it's, you know, do this or else, meaning if you just say else without an if statement associated with it, you know, R doesn't know what to do, okay? So to associate the else with an if statement, you have to put an else on the same line as the closing curly brace, right? Before we said, you know, if you only have one line for an if, the curly braces are optional. If you're going to use an else, you need to have the curly braces, okay? And then you can also throw in another conditional, so you can have an else if, and it will check another condition. So in this case, we've got an if, an else if, and an else. And we start off with the value 3, x equals 3, and it starts off, if x is less than 0, this is false, so it completely ignores this line of code, and it goes to the next part. So then it says, okay, well, that's not true, that's false, so we run the else, okay? Excuse me. And when we run the else, it looks at this and says, if x is greater than 0, well, this is true, okay? X is 3, 3 is greater than 0, so it runs this code, print positive, and then it finishes. Okay, it doesn't bother executing this thing because this part evaluated to true. Okay, so as soon as one of these things gets evaluated to true, it's going to skip the rest, right? Because the else's only get evaluated when the previous conditionals are false. All right, in this case, we've got x equal to 0. It looks at this, is x less than 0? That's not true, so it skips this. Else if. Is x greater than 0? Also not true. So this is also false. So it skips this line. And then it just says, okay, well, this was false and this was false. So I'm going to just do what's left over. I'm going to run this else statement and it's going to print out 0. Okay, and so this covers kind of all of our scenarios. Either x is less than 0 or it's greater than 0. And if neither of those are true, then x must be 0, right? Yeah. At least as far as real numbers go, that's what we have, right? Is I greater than or less than 0? You can't answer that because it's in the complex plane. Yeah. So, okay. So there we have that. Okay. We've got in this case we've got x equal to 3, and notice, you know, here I have some poorly written code. Okay. If x is greater than 0, print positive. So this is true, it's going to print positive, and because this is true, x is greater than 0, it's not going to run any of these else statements. So if I have else if x greater than 1, print bigger than 1. But this doesn't even get evaluated. It doesn't even check to see if this condition is true because this part was true. So as soon as this thing is true, all of these other else statements, they just get ignored. Okay, so the else's only get executed if the previous statement evaluated to false. Okay, so if you need something like this, this is not going to work. Okay, sometimes you have if and else statements where the only result that you want it to do is to do some kind of assignment operator, okay? So if you don't actually need it to run code, but you just need to assign a new value, then there's kind of a little bit of a shortcut statement called if else. So in this case, we have If x is equal to 5, then n will be, yes, the value yes will be stored into n, or no will be stored into n if x is not equal to 5. Okay, we can reduce this into if else x equal to 5, yes or no. And this just says if this is true, then it's going to take this value and store it into n. Otherwise, it's going to take this value and store it into n. This is just kind of the value that you're going to return and store. And you're not going to run additional code. Because sometimes all you want to do is just do an assignment based on a conditional. Okay, and if else is useful for that. Okay, we can talk about loops. All right, and I think you covered loops in Stats 20, but we'll cover them some more here. Okay, for loops are probably the most common type of loop in R. And what you do is you give it a vector, including any kind of vector. So and R sees lists as vectors as well. And what the for loop does is it just iterates through each element in the vector. Okay, so probably the most common vector you give it will be an integer vector 1 through 10 or 1 through 1,000 or whatever it is. Okay, that's probably the most common vector you give it. So when it runs, x is going to be 1, then it runs x is 2, x is 3, all the way until it reaches the end of that vector, x is 10. So in this case, we've got x in 1 through 10, cat x squared. So it says, okay, and then also a space. And so in this case, it's going to, first time it runs x is 1, okay, because here we have the vector 1, 2, 3, all the way up to 10. So it runs it for 1, 1 squared is 1, it cats that. Then it goes to the next element in the vector 2, 2 squared is 4, it cats that. Then it runs to the next element, 3, 3 squared is 9, and so on and so forth. Okay. No surprises here, right? Okay. Quiz? Not really. What would happen if instead of cat I used print? Print x squared. Instead of cat, yeah, what would happen? It would print them all on different lines, and we would have bracket 1 in front of them. Okay, so print kind of prints them as objects. Cat just kind of outputs straight to the screen. And if I didn't have this space here, then all of the numbers would get all pushed together. It would look like 149,162,536 something, right? So this is all those values would get just squished into 1 if I didn't have the space. If I had print, each value would appear on its own line with a bracket 1 to kind of indicate that it's a integer numeric vector there. Okay, so this is giving it a vector of 1 through 10. But like I said, I can give it any vector I want. So in this case, I'm going to create a list of 3 things. And the 3 things is a integer vector 1, 2, 3, a character vector A, B, C, D, E, F, G, and a logical vector of true, false. And I can just say for y in that list or vector L. And then when we run this, it's going to, first time, it's going to run through the first element in this vector, which is that vector 1, 2, 3. Then the second iteration, it will run it for the second element, which is the character vector A, B, C, D, E, F, G. And then the third time, it will run it for the logical vector true, false. So the code we're just running is cat the length of object y. So again, it runs it. It looks at the first element, 1, 2, 3. It cats that length, which has 3 elements in it. So it prints out a 3, or it cats a 3 onto the screen. Then it runs for the next iteration. It goes to the second element in the vector, which is the character vector with 7 letters in it. And it says, okay, this object has a length of 7, and it cats 7 to the screen. And then it does it for the last thing, and it cats a 2 to the screen. Does that make sense? Okay, so here we are passing not. So this is probably the most common thing that you pass it in when you run for loops. But this time we're not passing it an integer vector. We're passing it a list of different types, and it's going to go through each element in that list. Okay. At the end of this, if I ask, what is the value of y? What is the value of y? The value of y is this true-false vector. Yeah, I wanted to do. So here I go. I run that, okay? And if I ask what is y, or we can actually see it right there, because y is just the last thing it ran. Y is the vector true-false. Okay, here's one. We can load up the library data sets. Inside data sets, we've got state.name, which has the list of all states in the union. Okay, and so we've got Alabama, Alaska, Arizona, Arkansas, California. And then here we just say for, this is basically y or x, or in this case, we're going to call it state. In this vector state name, we're going to cat the state itself, which is the characters Alabama. And then we cat the letters HAS for the word has. And then the number of characters in this element, Alabama, so that's 7 letters. And then we say letters in it. And then we put a /n to say, go to the next line, okay? Otherwise, cat doesn't bother producing new lines, right? It just keeps going straight onto the screen output. So we do this, and then it iterates through each element in our vector here, and it says, you know, ends with California has 10 letters in it. Okay, great. When we run loops, a lot of times we want to capture the output, and we want to store the output somewhere. And when you do that, it's always a good idea to define, well, first of all, you have to define where you're going to store that output, but it's a good idea to define the place where you're going to store that output and with the proper size already. So in this case, I'm going to run 10 iterations. X is going to go through 1 through 10. And so I need 10 locations to store this. So I'm going to create an empty vector, or a vector of missing values of length 10. Okay, so this creates a vector of length 10, initially with missing values. And every time I run it, it's going to say into the first spot, store 1 squared. Into the second spot, we subset to the second location, store 2 squared. So on and so forth until it reaches the end. Into the 10th spot, store 10 squared. And that will give you kind of your best performance as far as storing results from a loop. Okay. I'll show you other examples. These are quote unquote bad examples, but they're not. In terms of efficiency, they're bad, but in terms of does it work and does it give me the results I want, they are okay, all right? And that's the most important part. As you're programming, the most important thing is to get the thing working. Once you get the thing working, then you can start worrying about efficiency, right? And you get better with coding, just like everything else. Every time you practice, you're going to get better with it, and so you can worry about efficiency after you get it right. It's much more important to be correct than to be efficient. Okay, so here's a bad example in that I just say I'm going to have my results. The location where I'm storing my results is just an empty vector. I just create an empty vector of length 0. And then, by the way, if I say results see this, and I did type of on results, what do I have? So if I just say results is see here, and then I say type of results, it's actually a null vector, but it's a little I know that's odd, but okay, and then I can. All right. Well, anyway, so I'm starting off with empty, and then I'm going to just take the current vector and combine it with the result x squared, and then it works, right? So the first time we combine with kind of the empty vector with 1, and then we get 1 squared. Then we go on to the next thing. It's going to be 1 combines with 2 squared, 4, and so on. And every single time, each iteration, we have to copy the current results vector into a newly redefined results vector. It works. We get the results that we want, but it's inefficient to run it this way. Another thing that's a little bit bad is that I start off with a vector. I just put in the value 0 here, and then I just say into position x, take the value, store x squared. Okay, and this will the problem with this is that on the third iteration, what it sees is a vector of length 2, and then it says, okay, in the third location, I'm going to store 3 squared, and so it has to resize the vector, which takes some computing overhead. Okay, so having to resize the vector is a little bit inefficient. Again, it works, and if this is the solution that came to mind in the beginning, that's fine. But again, as you get more experienced in your programming, you'll start taking more efficient methods, right? Okay, so that's what we have. Oh, and then just going back here, notice I stored NAs rather than zeros. Okay, I would recommend that if you're expecting numeric results, you might want to put in zeros, and that's fine. But the reason why I would pick NAs is sometimes your loop ends prematurely, and let's say here we expected it to run 10 times, but it's possible that for whatever reason maybe your code wasn't perfect, and so it stopped after 7 iterations. Okay, and then you wanted to do some analysis on those results. If you just had zeros, you would have 1 through 49 and then 0, 0, 0, and then if you ask what's the mean of that vector, those zeros are going to give you the wrong results, right? If you had NAs in there and you say what's the mean of the vector, because of those NAs, R is going to come back and say you've got missing values, right? And then you can explicitly tell R, okay, ignore the missing values, but it at least alerts you to the fact that you have some missing values there, okay? And so so it is recommended that you use NAs rather than kind of blank or zeros or the equivalent, because zeros can be added and subtracted and multiplied and be used in calculating the mean, but it's probably not what you want. By using missing values, it provides a little bit of a check to say, hey, you've got something missing when you ask for it to calculate the mean. All right, so that was 4 loops. Let's talk about some other loops. We've got the while loop, okay? The while loop will repeat until the given condition is false, okay? So here, we start off with the value I equal to 1. We set I equal to the value 1. We create a results vector. And then the while loop will run all the code inside the curly braces as long as this condition is true, okay? And when this condition is false, then it kicks out. So it starts off with, and so, if you write bad code where this condition is always going to be true, your while loop will run forever, okay? So you need to have something that's at least going to update, and the thing that's going to check has the possibility of becoming false. Okay, so when we run this, we start off with I equal to 1, okay? I is 1 less than or equal to 10? Yes. So then it runs the code in here. So into results position 1, we're going to store 1 squared. Then we iterate and we say 1 plus 1, so which is 2. We reassign the value of I to 2. Okay, it reaches the end of the code, and so it goes back to the top of the loop. And now I is 2 less than or equal to 10? Yes. Then into results position 2 stores 2 squared, 4. Then I is now 3, and it keeps going. Okay, down here it gets when I is 9, okay, into the 9th position, we're going to store 81. I becomes 10, okay? It reaches the end of the loop here. It goes to the top. Is 10 less than or equal to 10? That is true. Results into the 10th position, store 100. I is now 11. Okay, it reaches the end here, and it goes back to the top. Is 11 less than or equal to 10? That's a false. And so when that happens, it does not execute this code, and it's done with the loop, and then it prints this out. And so in results, we get 1, 149 up through 81, 100. If I asked R, what is the value of I at this point in time? What is the value of I? I is the value 11, right? Because the code gets executed when I is 10, and so it stores this into 10 squared, and then it updates the value of I to 11. And then when it evaluates, is 11 less than or equal to 10? That's false, and so it kicks out. So our loop will run, and then I will take on the value of 11. So I can just run this code here. So here's the while loop. When we run this, we can see the results is exactly that. And if I ask what is the value of I is the value of 11. Okay. Let's, what if inside sometimes we might make the mistake and we put something like this inside our code, okay? We put we set I equal to 1 inside our code. What's gonna happen if I run this code? It's gonna go on forever, right? So here we'll delete everything out. Okay, so if I run this code, it's running. It's never going to stop. It goes on forever. Okay, when I stop the code, what is the value of I going to be? Okay, it's gonna have the value 2, because what's going on is that, I guess it's possible that I stuck the code right in the middle here or something. But basically, we start off with I equal to 1. Okay, it's going to store 1 into position I. Then it takes into the results vectors, the first position, put in 1 squared. It updates I to 2. And then it goes back to the top. Is 2 less than 10? It is. And then it reassigns the value 1 to I. Okay, it overwrites that. And so now we've reset it. And so you can see the results vector just has a 1, okay? And it never got to the next position because every time I got changed to 2, it overwrote that value, okay? So you don't want to kind of override your counter inside your while loop because that's going to cause you problems, okay? So that one, it would have run on forever, and then you would need to tell R to stop. Okay, here's another type of loop, which is the repeat. The repeat loop will repeat forever, okay? It just goes on forever, and the only way you can get it to stop from going on forever is by including the keyword break, okay? So it's very important inside your repeat loop, you have a condition that will trigger the word break, okay? So here we start off, I is 1, and it's pretty much the same that we have before. We have a results vector, and then we repeat and we say results I, into position I, store I squared, then update I to be I plus 1, and then we have the condition if the value I is greater than 10, then break out of the loop, okay? So what will be, so we run it, it goes 1 squared, it goes on to 2, okay? When I is 2, this condition is false, so it does not execute break. And it goes on and it puts in 2 squared here. I gets updated to 3. Is 3 greater than 10? No, it's not. So break doesn't get executed and it runs. Okay, and then it goes all the way to 100. At the end of this loop, what is the value of I? The value of I is 11, okay? Because at I equal to 10, it's going to store into the 10th position in the results vector 10 squared. Then it updates I to be 10 plus 1, 11. It goes, if 11 is greater than 10, that is true, then it executes the break command. Okay? Prior to that, when I was equal to 10, it did not execute the break command, and it's only when I is equal to 11 that break gets executed. Okay, so it's when I is 11, break gets executed, it kicks out of the loop. And so the results vector has 10 values in it, and I has the value of 11. Yes, question?
This might have been already answered, but why for the board did you have the curly brace start on the same line, or start on another line, but all while repeat? Is it just kind of
Yeah, there's no significance there. Just, I don't know. I don't know why it's that way. Okay, yeah. You can have I could have put the curly brace immediately after the closing parentheses, like this. I can have it like this, and the curly brace just kind of associates several lines together. So yeah, it's stylistic. It makes little difference. In other languages, like Python, it does make a difference. But well, Python doesn't even use curly braces; it uses indentation. But okay. Special keywords: break and next. Okay, so break will end whatever loop it is. Okay, the loop that's running, when it runs into break, it quits that loop. Okay, if you can nest loops inside each other, so break will just stop whatever loop that you're inside right now. Okay, and then next ends the current iteration. So here we're going to go through the vector, integer vector 1 through 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we say if I mod 2 is equal to 0. So basically, if I is an even number, right? If I is divisible by 2 and leaves no remainder, then execute break. So what happens, and then, and if that's not the case, then we just keep going and we run the other code, and which is just going to be cat the value here. Okay. So here I is 1. This code is not executed because this is false. So it skips this part and it cats the 1. Then it reaches the end of the loop and it says, okay, I'll go to the next iteration, 2. If 2 is divisible by 2, that's true. So it executes this code, the break. As soon as it hits the break, it quits out of the loop. It doesn't execute anything after that. And so it just stops right there. Okay, I is 1. It cats the 1, then I becomes 2, and then it stops right there, okay? So if I asked R, what is the value of I at this point, I has the value of 2. Okay? On the next slide, I have the exact same code, except I replaced the word break with next. So the next here just says, don't stop the loop, but quit the current iteration. So same thing. We start off with a 1. This is false. So the next is not executed, and it cats the 1 onto the screen. It goes to the next. It reaches the end of the loop, so it goes to the next iteration. I is now 2. It runs the code. 2 is divisible by 0, so it executes the next. Okay. As soon as it sees the next, it goes to the next iteration of the loop. It doesn't bother running any of the code that comes after the next. So it says. It sees the 2, it goes to the next iteration, I is now 3. The 3, it goes here, this is false, so it doesn't execute this, and it cats a 3 onto the screen. Reaches the end of the loop, it goes to the next iteration, 4. And so on and so forth. And so this ends up printing the odd numbers, 1, 3, 5, 7, 9. At the end of the loop, what is the value of I? I is going to be the value 10, right? Because it goes through our vector 1 through 10, and then it reaches the end of the vector and it says, okay, I'm done, all right? So there's no instructions here that says like add 1 to I or anything like that. It just says the for loop just goes through the end of the vector. When it reaches the end of the vector, it's done. So it gets to the 10 and then it's done. I will have the value of 10. Okay, talking about for loops again. You know, we first had the example where we had y or whatever it said, you know, for y in list L, and so y took on the actual elements of the list. But instead, we could just use the sequence because this list has 3 elements in it. I could say for y in 1 through 3, and then just kind of modify my code a little bit to subset my list accordingly. And that's what these things, sequence along, and sequence length do. Okay, so these basically, here I'll just kind of show you. I could do 1 through length L. The list L has a length of 3, so 1 through 3 is 1, 2, 3. Sequence along L is exactly the same, and it does 1, 2, 3. Or I can do sequence length of length 3, and it goes 1, 2, 3. So these are just different ways of getting the vector 1, 2, 3. Or if you had a vector of length 25, it would go 1 through 25, basically. Okay, this is probably, you know, my default method is to just do 1 colon length of L. That's kind of the idiomatic expression that I use probably the most, but this is also very common. Sequence along L, it just takes whatever vector it is, it figures out the length, and it creates the integers 1 through that length. Okay, so here we're going to use for x in sequence along L, which is effectively just the vector 1, 2, 3, and then we say, okay, into the results vector x, position x, write down the length of L double bracket x. Okay, so then it goes through the first thing, and it says, okay, that has a length of 3. The next one has a length of 7, and the last one has a length of 2. So it gets 3, 7, and 2 gets input into our results vector. Does that make sense? Yes.
So wait, why can't you just use like x in L itself? Like,
X in L?
Yeah.
You could. That's what we did. Yeah, the first one back here we had for y and L, yeah. And we said cat the length of y. Okay.
Is there like efficiency, like if you use the
it's not an efficiency thing. It's sometimes you want to know the position. Okay, and so over here, where did it go? We just cat the length of y. But if I wanted to store this output 3, 7, and 2 into a certain position, I would need to have some way to kind of keep track of which position I'm in. Okay?
So and y doesn't do that in this one?
Y doesn't do that. Y takes on the values of these elements themselves. 1, 2, 3, 1 through 7, or A through G, and so on and so forth. So y, there's no numeric value associated with y here. Okay, and so sometimes that's actually very useful to us. So it's more, we might prefer to have kind of the numbers 1, 2, 3, and then subset our list L accordingly. Okay.
So in this case, x is the index.
X is the index, 1, 2, and 3 exactly. Okay, and so having that index is oftentimes very useful to us. Yes.
Why are we using double brackets?
Yeah, why are we using double bracket? What would happen if I used a single bracket here for here? Length of L, single bracket X. What would happen if I did that? So I'm saying results of X is going to be length of L, single bracket X. What would happen if I did that? Okay, so the single bracket, so just think, L single bracket 2, what would L single bracket 2 be? It would be a list of one item, and that item contains the letters A through G. Okay, and so if I did L single bracket X, what would my results vector be? It would be 1, 1, 1. Okay, because it's just saying, okay, subset the list to, you know, train car 1, train car 2, or train car 3. But if you look at train car 2 and you ask what's the length of this thing, it only sees one train car, and so it only has a length of 1. Okay? What we want is not the train car itself, we want the item inside the train car, which is a vector A through G, and we want that thing which has a length of 7. So that's why we're using the double bracket rather than the single bracket. Okay? Yes?
Would you use like loop to like go through each element in each like thing of the list, or how would you do that?
Yeah, you could. You could say it would be a lot trickier if you wanted to have a nested loop to go through each element in here. You would then probably have to do something like for y in the in that element. Yeah, exactly.
It would be like within L double bracket X.
Yes, yes.
Okay.
For y in L double bracket X, and then the first time it would go, y would be 1, then 2, then 3, and then the next time y would be A, then B, then C through G, and so on and so forth, and then you can do something accordingly there. Yes, so you could have a nested loop to iterate through each element there. That one you probably, well, I guess you could do a sequence along as well if you needed the index. Exactly. And you would need something flexible like sequence along, or the length of that thing. Yeah, exactly. Yes, you can have these nested structures. Okay, so we already covered this thing. These are just different ways of expressing the same thing. Okay, and just kind of a summary of all of this stuff is that all of these loops we've seen so far, we've built loops, but we could also have done this using simple subsetting or any of the apply function families, and those are generally going to be more efficient. But in the beginning, I think the way our brains pick up programming concepts, I think we pick up loops like there's like certain hurdles that you have to get across, right? Like some people struggle with loops and then they get the loop, okay? And then once you understand the loop, then like you see everything as some kind of form of a loop, right? But then I think once you understand loops, then you can understand vectorized operations such as the vectorized ones or the apply families. And so that's kind of the next hurdle. And if you can understand those, a lot of times that simplifies things and makes things more efficient, but it is another hurdle there, okay? Again, whenever there's multiple possibilities to answer the same question, the best one is the one you can get working, okay, correctly. And then after you get it working correctly, then you can worry about optimization and efficiency. And that way, as you're trying to optimize something, if you make a mistake, you can always go back to the less efficient but correct code. Okay, you never want to have efficient but wrong code. Okay, that's not useful. All right, let's talk functions. Okay, functions are very important. They we'll often have repeated operations that we need to perform on different inputs, and that's what a function allows us to do. Functions are always in the form, we name, whatever name the function is, we say we're going to take the function and we give it a list of arguments. These are the inputs to the function, okay? So just like a mathematical function, you have inputs and an output. For R, you have arguments going in, and then it's going to return an output. A function can only have one output, and that's the return object. All right, so you take multiple arguments in, you run code, expressions in there, and then it returns an output. The functions generally, you'll have curly braces, and then at the last line you'll have a return. But some of these things are also implied. If you only have one line of code, then you don't need curly braces. And if you leave off that word return, it's going to return the last thing that it evaluated. Okay, so here we're going to define f as a function. F is a function of x. What it's going to do is going to multiply x by itself, and that's what it's going to return. So if we, and just like any other object in R, we can throw f into a list. So we can have a list with f in it, and it gives me a list with f in it. We can ask what is the type of for f, and the way functions are stored in R, they're called closures. Okay, so a closure in R is basically a function. I don't know why they call it that, but that's what they call it. Okay. functions themselves can return other functions. The object we return could be a function, and I know that's weird, but it's possible, okay? You do not have to fully understand this slide. If you want to put a note, this slide is not critical for your understanding, that's fine. But here, we're going to say f2 is going to be a function, and the thing that f2 returns are other functions, okay? So it's going to return a function. So the input is a function of x, and the output will be a function of y. So here, we're going to take in the value 1, and what it does is it's going to create a function that effectively adds 1 to different values. So if I do 1, it's going to put 1 into the x, and now you have a function of y where you add 1 plus y. And so here, if I run add 1 on 7, it's going to output 8. If I have add 1 on 25, it's going to output 26. Over here, this part, f2 with the parentheses 4, it's going to create a function taking that value 4, and it's going to put the 4 right here. And what it returns is a function of y where we're doing 4 plus y. So in this case, if I have f2, the function of 4, and I run that function on the value 1, it's going to return 5. Okay, so I know it's a little bit weird, but functions themselves, the object it returns can be anything, and that includes other functions. Again, don't worry about this. This is not a functional programming class where we would do stuff like this. But this is a useful feature of R that can be handy. All right, we have the return values. And again, the function takes in the inputs through its arguments, and then it returns an object. Okay? And you can give it an explicit return. You can say return x times x, and that would be the explicit definition of what to return. Okay? Otherwise, if you don't have return in there, it's going to return the last thing it executes. So if you have a bunch of lines of code, that last line is the object that it's going to return, which is fine. If your function, if you put the return earlier on in the function, as soon as it hits that return, the function is going to stop, okay? It's not going to run the code that comes after the return, okay? Because the function, basically, it sees, its purpose in life to take in its arguments and return the value. And so once it has returned the value, it sees its, purpose in life complete, and it's not going to bother executing any of the other lines of code. So you might have like a condition somewhere in there, and it says, if this is true, then return this value. And then once that happens, the function is done, okay? And maybe that's what you want, but you have to be aware of that behavior. Okay. Like I said, you can only return one object, okay? So if you need to return different values, you have to combine those values together or group them together into a single object. And that's fine. When you run the function lm in R and you get a linear model, it returns a bunch of different values, but it has grouped all those things into a single list object, okay? And that's what we have to do. If you need multiple values returned, you have to group them together. So in this case, we're going to just take the function x, and we want to return 3 values, so we group them together using C. And so it's going to return x, x squared, and x cubed. And so the function run on the value 2 will return 2, 4, and 8. Here's something similar where what we return, we group everything into a single list. And so when we run f, it returns that one list, and it contains the values 2, 4, and 8. Okay? But again, a function can only return one object. So if you need to return more than one value, you've got to group them together into one object, like a list or a vector. In this case, because the function that we've run uses vectorized operations only, such as x, x squared, and x cubed, we can have vectorized inputs, and it will return vectorized outputs, okay? But if you have an if statement in your function, it's not going to work, right? An if is not a vectorized operation. If only takes in one true or false value, and so so that won't work. So if you so anything more complex, a function probably can't handle vectorized inputs, okay, if you've got if statements in there. So you've got to think of, what kind of values go into your function, what kind of operations you've performed there. When you define your function, here we defined it as a function of x, y, and z. We are giving the argument names, and then the order in which we've defined the arguments also kind of imply the order in which you are expecting these inputs. So when we say x, y, and z, and we give it the function 1, 2, 3, it's going to associate 1 with x, the first element, 2 with the second, which is y, and 3 with the third, z. And so here's the simplest function, which is just print out what it says, and x is x, y is y, and z is z. We paste those together, and we say x is 1, y is 2, and z is 3. This then allows, we can see then how the behavior works when if we want to change the order of the inputs, we can define z as 1, and x is 2, and y is 3, and we get that appropriate out. X is 2, y is 3, and z is 1. If you only define one of them and say y is 2, then r will match up the other things in the expected order. X will go with the 1. 3 is going to go with the next element that hasn't already been defined, which in this case is z. So we get 1, 2, 3. Okay, and then and if you give it an argument that is not part of your argument list, then it's going to kick back an error. Oh, I'm running out of time, but and then okay, I think this is easy enough for me to just throw up here. You can also give it default values inside the definition of the function. You say the function of x and y and z, where the default value of x is 1 and the default value of y is 1 and z is 1, so that if you call the function with none of the arguments defined, it's not going to error out, but it will use the default values. And you can then call the function with any of the values explicitly defined, and it will also function, and just substitute in the default values for the places that you haven't defined them. Okay, we'll end here for now, and then we'll pick up on scoping on Friday.